In this lecture, we will introduce transaction management. Modern computing environments are multi-user shared environments. There are many users using a database simultaneously. If we do not follow some rules, the users may interfere with each other. It may cause a lot data integrity issues. We want to use concurrency control to manage transactions in a busy multi-user shared environment to avoid data problems. In the meantime, we still want the database to perform well. So, what are transactions? Transactions are a logical unit of work. There may be many steps in the unit of work. All of those steps must either succeed or fail together. If the unit of work succeeds, the transaction is committed. The transaction moves the database to the next consistent state. If the unit of work fails, the transaction is aborted. The database is returned to the previous consistent state. A committed transaction cannot be aborted. An aborted transaction may be restarted by the system. A real-world example is to transfer $1,000 from our savings account to the checking account. There are two steps. The first step is to withdraw $1,000 from the savings account. The second step is to deposit $1,000 into the checking account. The two steps consist of a logical unit of work. The two steps must either complete or fail together. There are four very important properties of transactions. A, C, I, D. A stands for atomicity. There are many steps in a transaction. They must succeed or fail together. C stands for consistency. A committed transaction moves the database to the next consistent state. An aborted transaction moves the database to the previous consistent state. The database should always be in a consistent state. I stands for isolation. We use isolation to maintain data integrity in a shared multi-user busy environment. D stands for durability. A committed transaction cannot be lost, even there may be a later system failure. So, what are the data integrity issues? Here are some common ones. Lost updates mean a user could accidentally overwrite another user's update without knowing it. Dirty reads mean a transaction can see the intermediate results of other transactions. The intermediate results may not be correct. Non-repeatable reads mean in a transaction, the SQL code may read a piece of data several times. The results may be different each and every time. In some situations, it may cause problems. Phantoms mean an inserted record was later rolled back. Other transactions saw the inserted new record, but the new record never existed in the database. Other transactions cannot find the new record in the database. So, to other transactions, it was like seeing a ghost. We use isolation to maintain data integrity. Here are some commonly used isolation labels. Generally speaking, read committed is the default isolation label for database management systems. Serializable is the most restrictive isolation label. It avoids all the possible data integrity problems. The data integrity problems allowed by each level are also listed. Pessimistic and optimistic are concurrency control techniques. We'll learn more about them later. Again, concurrency control is the technique that we use in a multi-user shared busy environment to manage transactions to avoid data integrity issues. We use concurrency control to ensure that users will not interfere with each other when they do their work. There are two commonly used concurrency control techniques, pessimistic and optimistic. With the pessimistic concurrency control, we assume conflicts will happen, so we'd better be careful. We will take measures to avoid conflicts. On the other hand, with the optimistic concurrency control, we assume things are just fine. We don't need to worry about conflicts. Conflicts are very, very rare, but when it's time to commit a change to the database, we still want to see whether there's a conflict. If there's a conflict, we want to handle it at that time. Locking is commonly used by the pessimistic concurrency control. There are some common rules about locking. Share locks are used for read operations. Read operations do not interfere with each other, so shared locks can coexist. Exclusive locks are used to make a change to the database. Exclusive locks cannot coexist with other locks. Also, when we implement locking, a major consideration is the size of locking or the size of data protection. Generally speaking, the larger the locking size, the lower the concurrency level, the lower the system overhead. On the other hand, the smaller the locking size, the higher the concurrency level, and the higher the system overhead. We want to choose the most appropriate locking size that will work best with our applications. In other words, we want to make the best trade-off so that we can maintain data integrity and to have good system performance. Some common locking sizes are row, page, extent, table, and database. Deadlock is an impasse. In a deadlock, transactions are held by other transactions because transactions are waiting for resources locked by other transactions. In order to resolve a deadlock, the database management systems need to choose a transaction or transactions to terminate. In other words, the only way to break a deadlock is to terminate a transaction or transactions. Those terminated transactions are sometimes called a victim. Those terminated transactions will be restarted by the system later. Usually, deadlock management is transparent to users. The system will handle deadlocks automatically, but in a busy environment, especially in a busy production environment, sometimes the system cannot handle deadlocks promptly. It may cause a lot of system issues. In those situations, operator intervention may be required. There are some programming best practices that we can follow to avoid deadlocks. For instance, if we have several operations needing to lock resources, such as resources A, B, and C, we want them to lock the resources in the same sequence. For instance, they will all lock resources A first, then B and C. If they follow different sequences, like one locks A, B, C, others lock B, C, A, different sequences may cause potential deadlock problems. Again, the concurrency control techniques are used to maintain data integrity. The optimistic concurrency control techniques are commonly used for applications that have a lot read operations but very few write operations. With the optimistic concurrency control techniques, we assume things are just fine. We don't need to worry about conflicts. We will just let users do their work, but when it's time to commit a change to the database, we still want to check whether there is a conflict. If there's a conflict, we will just handle the conflict then. Again, we must make sure that we choose the appropriate concurrency control technique that can work best with our applications so that we can maintain data integrity and have good system throughput. This concludes the lecture on transaction management.